Chapter 2, Physical Measurements. In this chapter, the following topics will be discussed. 2.1, Importance of physical measurements. 2.2, Errors and uncertainties in measurements. 2.3, Techniques in measurements. 2.4, Common measuring devices. And 2.5, Glossary of this chapter. 2.1, Importance of physical measurements. Physical measurements are important for the following reasons. 1. To verify physical rules and laws. 2. To find the physical properties of a substance and to identify the physical substance with the help of these properties. 3. To calibrate measuring devices. Important to verify a physical theory. Physics is the natural subject that intends to generalize the physical actions occurring around us by means of mathematical equations and lingual statements. An equation or statement is accepted only if it is verified by experimental data. Physical experiments are based on the measurements of relevant physical quantities like mass, speed, acceleration, length, volume, time, etc. If a theory or postulate is verified by experimental data following the assumptions of the theory or postulate, then they are turned into either rules or laws. What is theory? Theory is the statement or idea to explain how something happens. Theory explains or describes how something happens. So when this theory is verified by experimental data, then it is called rule. And if this rule is verified or applicable in all situations, this is called law. A generally verified rule to all situations is called law. When an apple fell on Sir Isaac Newton's head, he thought that it could be the attraction of earth on the apple. So it was theory. So he thought and worked a lot on it and concluded his works by the following mathematical equation. F equals to G mm by R square. This capital M is the mass of the earth, small m mass of the apple, F force attracted by the earth on the apple, G is a constant which is called universal gravitational constant, and R is the distance between the earth and the apple. This is center to center distance. Newton then converted this equation into a lingual statement. Gravitational attraction between two matters is directly proportional to the product of masses and inversely proportional to the square of the distance between the masses. This equation and its corresponding lingual statement is called theory of gravitation. Experimentally, later it is found that this equation is also applicable to our solar system to describe the planetary motions. So, the theory of gravitation is then turned into a law called Newton's law of gravitation. Without experimental verification, science will not accept any scientific explanation. Important to identify and to use physical substances. A physical substance can be made of a pure element, or of a pure compound, or of a mixture of compounds. A set of physical properties of a substance is unique. By measuring its physical quantities, the substance can be identified. The physical quantities which are used to identify a substance are density, melting point, boiling point, solubility, specific heat capacity, elasticity, toughness, hardness, ultimate tensile strength, refractive index, reflectivity, viscosity, surface tension, electrical resistivity, capacitance, impedance, permittivity, permeability, half-life, etc. What are these physical quantities? We'll learn later. Scientists and lab technicians have measured these physical quantities. They have written this data in a data book which are available publicly. These data books are commonly known as data handbooks. Since different substances have different physical properties, by measuring one or more of these physical quantities, a physical substance can be identified. Engineers use this data in their design works to use physical substances. Physical measurements are important to calibrate a measuring device. Calibration means scaling the dial of an analog meter according to the standard laboratory measurements. Calibration relates the display quantity with the measured quantity. For example, an analog thermometer is made by pouring mercury in capillary glass tube having a bulb at one end and the other end is sealed. There are no marking onto the glass tube. It cannot be used now as a thermometer. There is an uncalibrated thermometer. There is a bulb. Mercury is poured into the capillary tube. Then this end is sealed, but there is no marking onto the surface of the glass tube. This is uncalibrated. Now this thermometer is placed in the melting ice. Because we know the temperature of the melting ice, which is 0 degrees Celsius at normal atmospheric pressure and temperature. So the level shown by this mercury when it is placed at melting ice is 0 degrees Celsius. Then this thermometer is placed on the boiling water. Water boils at 100 degrees Celsius at normal atmospheric pressure and temperature. It means that at 1 atmospheric pressure 101 kilopascal and water boils at this pressure, water boils at 100 degrees Celsius. So this way mercury level is marked as 100 degrees Celsius. Then the gap between 100 degrees Celsius and 0 degrees Celsius is divided into 100 parts, and each part is equal to then 1 degree Celsius. This is called calibration. The mercury level is marked as 100 degrees Celsius. This space between the two marks is divided into 100 parts. Each part is called 1 degree Celsius. Mercury in glass thermometer measures expansion in mercury column but shows temperature. This device, it cannot measure temperature directly. Basically it measures the length of the mercury column or expansion of the mercury column. This is the display quantity, and it shows temperature by means of calibration, through calibration. So temperature here is display quantity and thermal expansion of mercury is the measured quantity. Here there is a digital thermometer, thermistor thermometer. There is a sensor thermistor. Its resistance changes with the change in temperature. So measuring resistance, we can measure temperature. The building relationship between the resistance of this thermistor and temperature at laboratory is called calibration. Here there is a thermocouple thermometer. Schematic diagram of thermocouple thermometer. Thermo EMF across the metal wires vary with the variation of the temperature. So thermo EMF is measured by voltmeter. Corresponding temperature is measured by suitable standard thermometer. Thermocouple thermometer has two joints, two ends. They are made of two different metal wires. So this is iron wire, this is copper wire. Now if these two joints or junctions are kept at two different temperatures, we will see a voltage written by this voltmeter, and this voltage is called thermo EMF, which is related with the temperature difference between these two junctions. So the making relation between the voltage and or thermo EMF and this temperature difference is called calibrating thermocouple thermometer. The relationship between these two sets of data are related by a suitable equation which is set in the memory of the digital system. Finding the equation is called calibration. So physical measurements are important for verification of physical theories, identifying a physical substance, using physical substances during design time, and is important to calibrate a measuring device.